Hey broskies, it's me, Science Brad, and I heard you guys wanted to learn a little bit about exploring creation with chemistry, second edition by Dr. Wiley, Module 14. Let's go. Hello, and welcome back. If you're wondering what Module 14 is about, it's about kinetics, more specifically reaction kinetics, which have a lot to do with the reaction rate of reactions. The reaction rate is the rate of change of a product in a chemical reaction. And the way the rate of reaction would look in a mathematical form would be this. All right, and then to get the reaction rate, you gotta have a reaction to start with. And chemicals cannot react unless their molecules are all like up each other, like knocking each other around, like a giant chemical mosh pit. All the molecules, you can't have a reaction unless the molecules are colliding with each other. All right, so as long as the molecules are colliding with each other, there's a reaction. But there's a few ways to increase the reaction rate so you get a faster reaction, and some ways to decrease it, all right? So one of the ways to increase it, you should like knock that temperature up. You crank that heat, and those molecules go crazy. They start bouncing around even faster. It's like knocking each other, like bumping each other around like a crazy mosh pit, you know? Just like knocking each other around. Chemical reaction rate goes up. All right? You want to turn that dial down? You want to decrease the reaction rate? All right? Reduce the concentration of whatever you're using, the chemicals you're using. Reduce the concentration, less molecules to bump into each other with, reaction rate goes down. So you want to turn it back up again, increase the surface area. If you increase the surface area, molecules can mingle around a little bit more. Got some more room, mingle, talk to each other, knock each other around some more. Reaction rate goes back up, baby. On to the next section. Hello, and welcome back to Exploring Creation with Chemistry. I'm actually Brad's twin brother, Chad. We switched out because we're getting to the math part of it, and Brad was never the best at math. He's actually not the brightest in general, and his accent was getting a little distracting, so I figured it's best if we switch out. But anyways, I believe he left off talking about how to increase and decrease reaction rates. And that takes us perfectly into how to do a reaction rate math problem. As you can see, I've already gone through one here. So as we start off, we have the chemical reaction, and we have 2 ICl plus H2, and it turns into I2 plus 2 HCl. And it shows the trials run here. And when you do this problem, you can pick from any of the trials that you want. And the equation that you will use, this will be the equation. We have the rate equals the constant times the first reaction and the second reaction. And up here where the X and the Y are, those will be your reaction rate orders. And in some of the problems that you'll do, the reaction rate orders will seem similar to the stoichiometric coefficients. Some of them will be the same, but you should never trust that. You have to figure it out mathematically. Otherwise, you'll end up in big trouble when you're taking a test and you just try and use that. Sometimes you get lucky, but you should never trust luck. It's science. But the way that you can tell the coefficient here is you got to look at the trials. So in trial 1, there was equal amounts of concentration of each reactant. And then in the second trial, and then you can see the instantaneous reaction right here. And then for the second trial, they doubled the amount of the H2, but kept the ICl the same. And when they doubled this, the reaction doubled. So what you can tell from it doubling is the Y on here would be 1, because when they doubled it, which would be making the Y a 2, it doubled the reaction. And because
this stayed the same, but the reaction doubled, that also tells us that it is also 1. Because when they're both 1, 1 times 1, you get this one. But when you do these ones, 1 times 2, you get 2 times. So this is 1, and this is 1 for when they're equal. And as you can see down here, this adds up when both the reactions are equal and are twice the amount, the reaction is 4 times as large. So now that we know the x and the y, we can actually move on to doing the problem. So as you can see down here, we already know the r from up here, and you can just pick any of the trials, 1 or 3. 2 is the one where these are off, so I would either go with 1 or 3. And then I went with 1. And once you have that going, since you already know the r, you can rearrange it so that it's k equals r over the a and the b, which I did that here. I showed how you would fill that in, and then I rearranged it and filled it in. And then once you get your answer and you have the constant, this will be your constant. You can put the equation back into normal and have r equals, and then have your equation right here. And now that you know the constant, you will be able to figure out the reaction rate of any concentration of those chemicals for this reaction.
Hello, Science Brian, back to answer more of your questions. What's that? Do chemical reactions ever end? No, they don't. They just get really, really, really slow, and they keep going really, really slow forever. So they kind of end, but they keep going. But they just get so slow that you can't really tell if they're still going on. All right. I know I'm running a little short on time, so I'm gonna try to make these last few points pretty quick. Earlier, I mentioned that temperature increases the reaction rate. Well, there's actually a scale for it. And that scale for the heat increasing the reaction rate is for every 10 degrees Celsius you turn that baby up, the reaction rate doubles. So say your reaction rate is 2 m over s, and then you crank that baby up 20 degrees Celsius, that makes it 2 times 2, 4 times 2, which would be 8. 8 m over s if you increase it by 20 degrees. All right, and now for the final section of Module 14, we got the man, the myth, the legend, catalysts. All right, catalysts are the main man. They make the reaction go lightning fast. All right, you hear me? All right, so we've got a few different kinds. We've got heterogeneous and homogeneous. Heterogeneous catalysts are catalysts that are in the same phase as the chemicals. So say all your chemicals are in the gas phase. If your catalyst is in the gas phase, it would be a homogeneous catalyst. But say all your chemicals are in a liquid phase and your catalyst is a solid, it would be a heterogeneous catalyst. All right? And like I said before, just to define it a little more, catalysts increase the speed that the reaction happens at. So say a reaction that you're doing generally takes like about 20 minutes. But say dinner's in 10 minutes and you're like, oh no, I only have 10 minutes, I don't have 20 minutes. Well, you find yourself a catalyst, chuck that baby in there and it's done in 5 minutes. And that's how catalysts work. Wait, don't go in, I forgot. I was gonna mention it earlier because I forgot this too when I learned it. I don't have my sunglasses on. But catalysts do not get used up in the reaction, all right? So you throw that sucker in there, so you're done by dinner. You got, after 5 minutes after that reaction is done, that catalyst is still gonna be in there. It's not gonna be used. Catalysts do not get used up in the reaction. Knowledge. Alrighty now, hustlers. Our time is up today. Used up all time, gave you as much knowledge as I could on chapter 14 in the time that I had. Science Brian is heading out. Don't forget to like and subscribe. Alrighty, I've got one last thing here for you guys. It is not Science Brad anymore. I worked very hard on this presentation,
but I couldn't have done any of it without Breanna and Caleb's slides. I got all of my information that I used from their slides. I'm putting their slides in the link really quick, and so make sure to check those out, because my presentation helped, but sometimes it helps to look at this stuff visually too. So don't forget to check out their slides. They work very hard on them. And then also, one last thing. I did kind of a crazy video because we've been locked in our houses for 2 months, and I think we could all use a change of scenery, because when you've been locked in a house for 2 months, why wouldn't you want to see a guy in sunglasses and a sun hat in his basement at 12 in the morning rambling about chemistry? Like, how is that not going to make your mood better? And then also, I just want to leave a quick thanks to Mrs. Dale for teaching me for, I think, 4 years now. Maybe it's been 3. I've known her for so long. I can't remember when she was teaching me and when I just knew her. But I just want to leave a quick thank you to her, because she's taught me through all of high school, and I am a senior now, and I'm going to be going to college for electrical engineering, and I might have never figured out that I wanted to do that without her physics class. I can't talk. And she just taught it so well, and it made me realize what I wanted to do. So just thank you, Mrs. Dale, for being such a great teacher.